Okay, we're almost at the end here of the Chemistry 3202 review. This is Lesson 4, Unit 4, Section 2, Faraday's Law. All right, so let's have a look at what Faraday has to say. Okay, here's a little picture of Faraday, and I've got him pimped out a little bit here. This is Michael Faraday, and any of you guys who've done any physics and whatnot, you've become familiar with some of his work with magnetism and electromagnetics, electricity calculations, current, etc. Faraday's Law is dealt with on page 790 of your text, and there's a few related questions there. And generally on the public exam, there's always a calculation. Generally at the end, one of the last questions, long answer. But sometimes if it's not long answer, then it's definitely going to show up as a multiple choice. So I also have here a nice little picture of a chopper motorcycle. And what we're going to look at is on all these popular TV shows, you see these motorcycle places where they're tricking out these motorcycles, and they're putting chrome plating and gold plating and fancying up the bikes to make them real nice and shiny. Well, without Faraday back in the 1800s, without his work, this probably wouldn't be possible. All right, so Faraday's motto, I'm going to give him the motto, "Let there be chrome." Okay, and we call him the Chrome Meister, and that's the Orange County Motorcycle Shop there. Anyways, let's go and see what Faraday has to say about chrome plating stuff. All right, so there's Faraday in his shop back in the 1850s, and there's his tricked out little motorcycle that he's got there. But in any case, one simple little tiny outcome here, and we're going to look at how these calculations are done. So this is the general idea of what Faraday's work is all about. Now again, we're oversimplifying it a little bit here, but keep in mind that this is generally how it works. Now let's suppose we had a metal spoon. So let's say we had a piece of, an iron spoon or something like that, and we wanted to silver plate it. Okay, well what we're going to do is we're going to have a source of silver here, silver metal. Okay, so the silver is going to be one electrode, and the spoon itself is going to be the other electrode. So what's going to happen here is we're going to hook up a power source, and in this case I've got the negative terminal of the power source hooked up to the spoon, because that's where I want to see the reduction of the silver on the spoon. Okay, so what's going to happen here is as soon as I hook this up to my power supply, the electrons are going to start pushing onto the spoon, which is going to make the spoon negatively charged, which is going to attract the silver. And what we're going to start seeing here is the reduction of silver by that power supply to produce silver metal on the spoon. On the other electrode, we're going to have this in an aqueous solution, and what you're going to see on the other electrode, you're going to start to see oxygen gas bubbling up, because you're going to see the oxidation of water. All right, we're not interested in that. What we're interested in is what just happened on the spoon. So on the spoon, what we're going to start seeing is we're going to start seeing a very light coating of silver starting to form on the spoon itself. All right, and what we've done here is we've electroplated or silver plated the spoon with silver. So we put a very light coating of silver on this electrode. In the meantime, oxygen gas is being bubbled off. And as the silver is being consumed here, so we might have like silver nitrate solution, as the silver is being consumed, what you're going to start seeing then is you're probably going to see the oxidation of silver. That's what you're going to see. You're not going to see water, are you? Okay, because as we look at that, silver is above in both cases. Right, so you're not going to see the oxidation of water. You're actually going to see the oxidation of silver. So perfect. Even better, because silver metal is more reactive than the water. So what you're going to see is the oxidation of silver on this electrode to produce silver ions, which is replacing the silver that's being consumed here. And as a result, what you're going to start seeing is the silver is going to start to disappear. Okay, so the silver electrode is going to start getting smaller here, and the more we allow this to go, the more silver that starts to get consumed here. So what we see is all that silver is starting to stick on the silver spoon. Now, the longer we leave it in the solution with the electric current passing through it, the more silver is going to start clumping onto the spoon. If we leave it long enough, we're sort of going to see a great big clump of silver there, and it's not going to be very nice. So we just want a very light, thin coating here to plate out the silver. All right, so that's how they do that. So applications of this could be, gold plating, silver plating, chrome plating. We have to watch the electrolysis of water here if water is present. But if water is going to be a problem, then we can, create the environment differently so that we don't have to have water involved there. The other thing we do here is if we have found some trinkets in the ocean, like say we found a sunken treasure, some pirate treasure, and we suspected that we had some gold doubloons, right, gold coins, and we wanted to clean them up, this is the method they would use to clean them up. All right, they would actually, instead of having a hunk of silver here, they'd actually have the gold coin here, and you'd get the oxidation of whatever surface material would be on the coin or whatever type of material it would be. All right, so if there's a buildup of metal ions there, they would get that cleaned up that way. So real nice way to do it. Now what Faraday did, Faraday looked at the calculations to say, okay, this is going to be dependent on how long the spoon is in the solution. It's also going to be dependent on not so much the voltage, because the voltage that's required to do this, we can get that voltage from the table. That's not a problem. But it's going to be dependent on the number of moles of electrons. The more electrons that flow down through this spoon, the more silver you're going to get plated out. So it's going to be a function of time and a function of the current, which is dependent on the number of electrons. So Faraday did the work here, and what he came up with was a bunch of numbers. And he basically came up with this idea of saying, okay, the electric charge of what he came up with was saying electric charge by definition is the amount of electrons flowing past a given point for a given amount of time. And he gave this a unit and he called it a coulomb. So 1 coulomb would be 1 mole of electrons flowing past a point in 1 second. We compare this to be an ampere or an amp. You guys have heard of an amp before. Like you might have a 15 amp fuse in your house. If you trip your curling iron or something like that, trips the fuse, it's a 15 amp fuse. So once you go over that current, the fuse would trip. So that's what we're referring to. So 1 amp, according to Faraday, is defined as 1 coulomb of charge that flows past a point in 1 second. Okay? And he gave us a formula here that says Q equals IT, where Q is going to be the charge in coulombs. I is going to be representing the current, 1 amp, 2 amps, 15 amps, like that. And time, of course, is always going to be in seconds. Sometimes we'll give you the time in minutes or hours. You'd have to always convert to seconds. Now we also created another term here, which he called a Faraday. Like, how convenient is that? Oh yeah, I just invented something. I'll call it after myself. All right. Well, he called this the Faraday, and he said the Faraday is a relationship that shows the number of electrons as compared to a coulomb. All right. So coulomb is simply the amount of charge. The Faraday is going to represent how many electrons cause that charge. So what he came up with was a constant value that he's calling Faraday's constant, and it's a value of 9.647 times 10 to the 4 coulombs per mole of electrons. And then he gave us this nice little convenient formula where he said Q, the same Q that we had up here, Q is now equal to the number of electrons that are responsible for that charge, so NF. Q is the charge, N is the number of moles of electrons, and F is Faraday's constant. Now, do you have to remember that nasty number? Not really. What I really want you guys to remember are these two equations. Q equals IT and Q equals NF. Okay, the numbers and the formulas are given on the periodic table in your public exam, right? Q equals IT, Q equals NEF, and the value of F right here, 96485. All right, so 96,485 coulombs per mole. That's the value I want you guys to use. So let's do a calculation to see what Faraday was talking about here. Okay, here's a problem. It says we want to do an electroplating of aluminum metal, and we're going to do it in molten aluminum chloride because we don't want to have water interfering, right? So we get rid of it by saying let's melt the alumina at very, very high temperatures. So we're going to have free-moving aluminum ions and free-moving chloride ions. We're going to apply a current of 500 milliamps for 1.5 hours. So what we're looking at here is the idea that we're going to write down what we're given. We've got a mass that's unknown. We've got a current 500 milliamps, and we've got a time for 1.5 hours. What we want to do is we want to represent that as amps. So I'm going to divide that by 1,000 to get 0.5 amps. Now we know that 1 amp is 1 coulomb per second. So if we have 0.5 amps, that means we're going to have 0.5 coulombs per second. Let's go back here, okay? Because we know that 1 amp is defined as 1 coulomb per second. So I should write that here. 1.0 amps equals 1.0 coulombs per second. So in our problem, we've got 0.5 amps, so that means 0.5 coulombs per second. We've got a time of 1.5 hours, and we always want our time to be in seconds. So in this case, it's going to be 60 minutes per hour, 60 seconds per minute. So this works out to be 5,400 seconds. Everything has to be in seconds. So we want to calculate the mass of aluminum that's been produced here. So the very first thing I'm going to do is I'm going to look at this and say, okay, we can calculate our number of coulombs. Q equals IT. IT. So 0.5 times 5,400 works out to be 2,700 coulombs. From the number of coulombs that we've just calculated, we're now going to calculate the number of moles. You see where we're going with this. Q equals NF. I want to figure out the number of moles, so N, number of moles of electrons, is going to be Q over F. We plug our values in. Q we just found out up here. Faraday's constant, 96,485 from our table. And it works out to be 0.02798 moles of electrons. So what does that have to do with anything? Well, if we're going to reduce aluminum ions, we're going to be looking at this equation right here. Aluminum ions from the molten aluminum is going to have a 3+ charge. We need to use 3 electrons for every 1 mole of aluminum that we're going to make. So now that we know the number of moles of electrons, we can easily do a mole ratio to find the moles of aluminum, and hence the mass of aluminum. So we're going to do our little mole ratio here and say, all right, the number of moles of aluminum is equal to the required ratio over the given times the moles of electrons. The required is 1, the given is 3. So what we're saying is for every 1 aluminum, I need 3 electrons. So there we go. So we were given the number of moles of electrons, so the ratio is going to be 1 required over 3 given. So it's going to be 1/3. So we get 0.009328 moles of aluminum. And from that, now we can calculate the mass of aluminum. Mass equals N times big M, the molar mass. We get that from the periodic table. And for that period of time, for 1.5 hours and 0.5 milliamps, we get 0.25 grams of aluminum plated out. So in this case over here, if this was a molten aluminum here at very, very high temperature, then we would get the aluminum being plated out on the object that we wanted it plated on. Okay? So there we go. Here's another type of question. In this particular question, they're asking us, okay, let's find the time this time. Let's calculate the time. They're giving us the mass that we want to be plated out, and they're giving us the current that this is going to be applied. So there's going to be a 1.55 amps of current applied, which works out to be 1.55 coulombs per second. Now, we're looking at this and we're saying we want to plate out some silver on the cathode, just like we did in the example before. So the redox reaction for this is going to be the reduction of silver. And this is real convenient because it's going to be a 1-to-1 ratio. So the number of moles of electrons is going to equal the number of moles of silver that's going to plate out. So how do we go about finding this? Well, okay, let's figure out what we got here. we can figure out our number of moles of silver by simply saying N equals mass over molar mass of silver. So we know exactly how much silver we want, so we can convert that to the number of moles. Works out to be 0.008575. Now that we have the moles of aluminum, we can figure out the moles of electrons. Moles of electrons is based on the mole ratio. Number of moles of electron required over given, 1 to 1. We're required electrons, we're given silver. So it's a 1-to-1 ratio. So we've got the same number of moles of electrons. Okay, now that we know the number of moles of electrons, we should be able to calculate the amount of charge that represents, because Q equals NEF, number of moles of electrons times Faraday's constant. So NEF, 96485 is my value from the table. You ever have to remember that? Get it from the table. Works out to be 827.37 coulombs of charge. And we know that if we want to find the coulombs of charge, or we have the coulombs of charge, then we can say that Q equals IT. Now we're going to solve for T. T equals Q over the current. We put our values in, and lo and behold, we get 551.85 seconds. Now the question doesn't say how many seconds are we going to have it hooked up for. The question is asking us how many minutes is this going to be hooked up for. And the minutes, of course, are simply going to divide by 60 to get 9.19 minutes. There we go. So everything is related to the number of moles of electrons. Everything we do here, we're trying to go through to figure out how many moles of electrons. If we know the number of moles of electrons, then we can easily find the time or the current. If we know the time and the current, we can easily find the number of moles of electrons, and therefore we can find the mass. Every single one of these questions is bouncing around these formulas. Here's another example. This time the question's saying, we're going to do the electrolysis of nickel, but this time it's the nickel that's being consumed. All right, so nickel 2+ is being produced. So let's set the stage here. In this example we did here, we just calculated how much silver was plated out on the spoon. The question we're asking you here now is, how much of this silver is going to be consumed? I'm going to weigh this electrode before I do my electrolysis. I put it on for a few minutes, an hour, whatever the time is, and I start to notice that my nickel electrode starts to get used up. When I'm finished, I turn off the voltage, I take my electrode out, I weigh it again, I figure out how much just disappeared. All right, so I'm interested now in what the loss of the mass of the anode is going to be. In the other examples, I was looking at the gain in mass of the cathode. So here we go. So in this particular example then, we're looking at the equation whereby the nickel electrode, the anode, is being consumed. So it's producing, for every 1 nickel, we're producing 2 electrons. So we want to figure out how long we have to figure out what current we want to use here. So we're given the mass of the nickel that was consumed. We're given the time, it's 35.5 minutes, which works out to be 2130 seconds. And we need to figure out the current. Okay, well, if we need to figure out the current, we're going to use this formula down here, Q equals IT, rearrange it so the current I is going to be found by saying it's coulombs of charge over the time. We know the time, we just don't know the coulombs of charge. Can we find the coulombs of charge? Absolutely. Coulombs of charge is found by saying Q equals N, number of electrons, times Faraday's constant. We know Faraday's constant. All we need to find is the number of moles of electrons. And we look at this and say, hey, that's not a problem. If we can find the number of moles of nickel, then we can easily get the number of moles of electrons, because it's going to be twice as many. It's a 1 to 2 ratio. Can we get the number of moles of nickel? Absolutely, because we know its mass. So the number of moles of nickel is going to be mass over molar mass. All right, plug our values in. 1.2 grams divided by the molar mass of nickel from the periodic table, and it works out to be 0.02044 moles of nickel. Our mole ratio is saying we want required as electrons, so it's required over given, so 2 over 1 times the number of moles of nickel, twice as much. we get 0.04088. Now that we know our number of moles of electrons, now we can get our coulombs of charge. Q equals Ne times Faraday's constant. Get that value from the table. And we get 3,944 coulombs of charge. Now that we have our coulombs of charge, we know how long we applied that for, we can figure out our current. All right, so it's 3,944 coulombs being pushed through in 2,100 seconds, and therefore we get a current of 1.85 coulombs per second. We don't like expressing current as coulombs per second. We like expressing it as amps. So that means 1.58 or 1.85 amps. All right, there we go. Why would we want to know that? Well, if you were in the Orange County motorcycle shop, or you were in a shop where you were doing electroplating, you'd have to know exactly what to charge that person. You can't just say, I'm going to stick it on for 5 minutes, whatever comes out, comes out. You have to know exactly how much you're putting on, and you know the cost of nickel and whatnot, and so you can figure out exactly how much nickel was plated out, or chromium, or gold. We know that gold is like $1,500 an ounce, very, very expensive. You don't want to stick that on and forget about it and go away for lunch and come back an hour later, and all of a sudden you got this set of motorcycle handlebars that are like 3 inches thick, and they got all this gold plated out on it, right? So they can actually figure out how long. They know exactly how much nickel they want to put on here. They know exactly how long they want to put it on for. So now they want to say, well, what should I set the current at? And how long do I have to keep it on for? There we go. Last but not least, and I say not least because this showed up twice on 2 previous public exams. And it's a bit of a nasty little question here where they're trying to get you to think about what's going on. That's those level 3 type questions, isn't it? At first glance, you look at this and say, yeah, this is a real simple little Faraday's Law question, right? Because they're giving us the mass that is going to be increased by, so a titanium cathode that's going to get 2.35 grams heavier. We know how long we have it on for. It's 36.5 minutes. So that works out to be 2190 seconds. And we know what the current is. So the question's saying, what's the charge on the titanium ion? Now you might say, well, titanium, that's not on my redox table. Oh no. If I look at the periodic table, there's given me 2 possibilities. It's giving me a 4+ and a 3+ for titanium ions. So we're saying, oh no, which one do we use? Well, that's the problem. They want you to figure it out. Titanium is one of these multivalent metals. It's possible for it to have 2 or more different oxidation states. So in this case, they're listing a 3 and a 4+. So we got to figure out what oxidation state the titanium ions are in. So we're looking at this and we're saying, oh, titanium, we're unsure of what the charge is on that titanium, so I'm going to call it N, N+. Now, if this was titanium 2+, that means it would require 2 electrons to reduce it. If it was titanium 3+, it would take 3 electrons to reduce it. If it was 4+, it would take 4 electrons. So, if we could figure out the ratio of the titanium metal to the number of electrons, then we could figure out what the mole ratio is, whether it's a 2:1, in which case the charge would be 2+, or if it was a ratio of 3:1, then it would be titanium 3+. If it was 4:1, then it would be titanium 4+. So in this question, what they're really asking you is to find the ratio of the electrons to the moles of titanium. Let's have a look at it. So, if we want to find the ratio of the moles of electrons to the moles of titanium, we want to be able to find the moles of each. So we can easily get the moles of electrons here, because we're going to say Q equals IT. We know I, we know T. So therefore we can get our coulombs of charge. It works out to be 14,000 coulombs. From that, we can figure out the number of moles of electrons, because Q equals NEF. We know Q and we know F. It's a constant. So we can figure out our number of moles of electrons. 0.1475 moles of electrons. Doesn't look anything good yet, does it? So we've got our moles of electrons. What we need to get now is our moles of titanium and figure out the ratio. So the moles of titanium is easy enough to get because they gave us the mass here. So the mass of titanium divided by the molar mass of titanium metal. And what do we get? We get 0.04906 moles of titanium. Okay. Now we're saying it's the ratio of the moles of titanium to the moles of electrons. Whatever this ratio is, if it's 2 to 1, 3 to 1, 4 to 1, then we know what our charge is on the titanium. So if you like to see this as a little mathematical representation, that's what we're talking about in terms of the mole ratio, right? It's the number of moles of electrons equals the required moles over the given times the number of moles of titanium. So what I'm going to do is I'm going to bring the moles of titanium over to this side so that it can represent our ratio. So the ratio of the electrons to the titanium is going to work out to be 0.1475 divided by 0.0496, and it works out to be a nice round number, 3.00. So we now know the ratio of electrons to titanium. It's 3. So we now know that we have titanium 3+. There you go. And that's it. On the public exam, one of these 4 questions could be asked. They could ask you to find the mass. In the next example, they could ask you to find the time, or they could ask you to find the current, and in this case, they're asking us to find the charge. All right, so 4 different examples, 4 different possibilities. Make sure you can do these. Go and have a look at some public exams here, see what types of questions, multiple choice and whatnot. There's lots of them there. And check out these textbook questions, of course, and fire some of these off to your online tutors. And good luck. We're almost at the end. One more STSE to do. All right, see you later. Bye-bye.